what does it really mean for an AI to think? Today, we're diving deep into database fundamentals, the primitives powering the intelligent enterprise. Every transaction, real-time dashboard, and ML prediction rests on a database. Today's data systems must be global, always on, and infinitely elastic. The fundamental consistency, isolation, durability are no longer hidden. They're the strategic lever for AI, IoT, and edge computing. The database is not a commodity. It's the core infrastructure primitive that determines whether your services meet SLOs or silently fail. From ACID to base and back again, the industry relearned that correctness matters. The modern database stack is the new operating system for data. But here's where it gets interesting, the breaking point. Legacy architectures fail. Single-node databases max out on vertical scale. Writes bottleneck on a single leader. Adding read replicas introduces replication lag. Sharding application logic fractures transactional boundaries. ACID guarantees evaporate. Even with distributed caching, cache invalidation is a full-time job. Joins across shards are impossible. Kubernetes operators can't fix a monolith's inability to scale writes. The result: fragile systems, manual operations, and a ceiling on innovation. When operating the database consumes more time than building features, the fundamentals are broken. So what's the real problem? Let's talk about the root cause, denying the partition. The CAP theorem states that during a network partition, a system must choose between consistency and availability. Legacy databases were designed for a pre-cloud world with reliable LANs. They ignored partitions, then defaulted to inconsistency or downtime. Workarounds, eventual consistency, dual writes. Compensating sagas add complexity without solving the fundamental tension. The cost of eventual consistency is hidden. Data anomalies surface weeks later in analytics. A generation of applications accepted data loss as normal. Data loss is never acceptable. This raises a critical question: break through the new primitives. Disaggregated compute and storage. Consensus-based replication via Raft. Distributed timestamp oracles. Serverless, multi-tenant compute pools. These primitives shatter the old trade-offs: strong consistency, global scale, and zero downtime operations are no longer at odds. Separation of concerns enables independent scaling, live upgrades, and instant failover. Timestamp Oracle hybrid logical clocks combine physical time with logical counters for causality. This isn't a better database. It's a fundamental reset of the database operating model. Now let's zoom in on system architecture, the layered stack. Query layer, stateless SQL processors, autoscaling, transaction manager, global ordering, MVCC, lock table, storage layer, shared object store, S3, GCS with write-ahead log on fast disks, MVCC via immutable files, garbage collection reclaims old versions, metadata and coordination, Raft-based control plane for schema, membership, shard map. Each layer scales independently. Compute nodes are ephemeral. Durability is in the storage layer. Decoupling allows rolling upgrades without data migration and separates billing for compute and storage. Layered telemetry per layer logs, metrics, traces enables root cause analysis. Here's something most people overlook: storage engine, the write and read path. LSM engine writes land in memtable and wall, flushed assorted SS tables, compacted in levels, optimized for high write throughput and large scans. Bloom filters skip unnecessary reads. Compaction merges and reclaims space. Strategy, tiered, leveled, balances read versus write amplification. B-tree engine, pages organized by key, updated in place with buffer pool caching, optimized for low latency point reads. The choice impacts latency tails, storage amplification, and compaction overhead. A modern database often implements both, letting the workload decide. Think about this for a second. Transaction engine, ACID at scale. MVCC generates immutable versions per write, enabling lock-free reads at a consistent snapshot. Conflict detection uses optimistic concurrency or pessimistic locking. Two-phase commit combined with a global timestamp ensures strict serializability across distributed shards. Durability via synchronous replication to a quorum of replicas. A distributed deadlock detector resolves cyclic dependencies. Version vectors track causality across partitions. Isolation levels are precision tools for performance correctness trade-offs. And this is where things get complex. Query execution, from SQL to distributed plan. Parser builds an AST. Binder resolves names and types. Optimizer explores join orders, index selection, and push down using statistics, cardinality sketches, histograms. Cost model selects the cheapest plan. Executor runs a DAG of fragments, scan, filter, aggregate, join, limit. Data flows between nodes via exchange operators. Vectorized execution processes batches, maximizing CPU. Adaptive execution can change join strategy mid-query if estimates are wrong. One bad estimate turns milliseconds into minutes. But here's where it gets interesting: coordination. The Raft control plane. Raft replicates the metadata log across nodes. Linearizable reads and writes for schema changes, shard assignments, timestamp issuance, linearizability for metadata, serializability for transactions. Leader leases prevent dual leadership. Fencing tokens block stale writes. Automatic shard rebalancing is a metadata transaction. Failover completes within seconds. Consensus eliminates split brain entirely. The coordination layer ensures the distributed state machine converges under node failures and network delays. So what's the real problem? Let's talk about developer workflow, database as code, declarative version-controlled schema migrations, branching instant database copies for development and testing. Time travel queries enable point-in-time recovery and data debugging. Online schema changes with no downtime. Observability metrics via open telemetry. CI/CD pipelines validate schema changes before production. Schema linting prevents anti-patterns. Feature flags for gradual rollout. Database per branch for true isolation. The database becomes a programmable platform, not a black box. IDE extension shows query plans inline. This raises a critical question: production impact, resilience by default. Auto-scaling absorbs traffic spikes within seconds. Multi-region active-active topology with strong consistency and low latency reads. Online upgrades without interrupting transactions. Self-healing. Failed nodes replaced automatically from stateless images. SLO-driven P99 latency 10 members globally. Chaos engineering tests node kill, network partition, disk failure run in production with no impact. Continuous verification checks data integrity via checksums. The database operates like a cloud service, fully managed, predictable, boring. Now, let's zoom in on future, autonomous and edge native. Learned indexes replace B-trees with models that predict key locations. AI-based query optimizers learn from past executions, reducing planning time. Edge-native databases synchronize with eventual consistency, converging to strong under quorum. Autonomous tuning, no knobs. New storage hardware, NVMe persistent memory, forces reevaluation of LSM versus B-tree. The fundamentals adapt. Serverless and AI will make internals invisible, but ACID ordering consensus persists. The line between database and application blurs. The fundamentals of state management remain. eventually databases design themselves.